Hello again, everybody, and welcome to another Geo-Institute live stream. It is our final live stream of 2025, our 53rd of the year. That's a record. We've never done that many in a year. So if you were here with us for one or two or all 53, we just want to say thank you for being here. It is our Thursdays at 2 most of the time. You can set your watch by it. We're probably going live with something really good. We appreciate it. My name is Brad Keeler. I'm the director of the Geo-Institute, and we are thrilled for our final GeoStrata Extra of 2025 to be joined by a legend. We'll be going over to that presentation in just a moment. First, a few housekeeping things. If you don't know anything about the Geo-Institute, after you watch this today, you should head over to geo-institute.org, and there you will find out all kinds of things about us, including that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And if you like what you see today, and I think you will, I feel really strongly that you will, you should click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. Before we get to the presentation today, we must acknowledge something that happened the other day, the horrific Bondi Beach shooting, which killed over a dozen people in Sydney, just miles from where our guest is right now in Australia. There is not much we can say or do, it feels like at this point, just to say that we are all with the people of Australia as they make it through the aftermath of this horrific event. And we must say, too, if you or anyone in your family ever experiences any feelings of violence, even to yourself, please call and get help. Everyone around you will appreciate it. And I'd like to have just a quick moment of silence for the victims of the horrific shooting the other day. Thank you. And now, GeoStrata Extra. Again, it's the final one of 2025, and we brought out one of the big ones for this one, all the way from Australia. Harry Poulos is going to present today on his two pieces in the current issue of GeoStrata, which you can access by going to readgeo.com. Hopefully you have it in your mailbox, but if not, just head over to readgeo.com. It's got an amazing purple tinted color this time. Fantastic to look at, and I promise you the content inside is just as good. And here to tell you a little bit more about what you're going to see today is GeoStrata editor Ken Fishman. Ken, thanks for doing this today.
Oh, thank you very much. I'm going to share my screen here. Can you guys see that yet?
Yep.
So the issue, as Brad mentioned, is a theme related to foundations for super tall buildings. There are 6 articles included in this particular issue. And the articles go through and they discuss a little bit about the history of tall buildings, some of the local practices that pertain to China as well as San Francisco, and then a little bit on design and construction details, including soil structure interactions, supportive excavations, groundwater control, and there's Harry's paper that discusses a little bit about interactions between the foundations of tall buildings, and he has also a commentary talking about limitations that may apply to tall buildings. So this is just an image showing Harry's "As I See It" or commentary, and then this is the article that is called "The Urban Forest." that gets into the interactions between the different buildings. I also just wanted to reference that, as we know, Professor Poulos has a few books, and one of them is actually Tall Building Foundation and Design. I had the opportunity to kind of go through this a little bit in preparation for this particular issue, as well as this GEOSTRATA Extra. And it's a very, very good book, quite comprehensive, goes into a lot of details of the process for foundation design. I think if you get a chance to take a look at this book, you would find it very interesting. And we all know some of the classic texts that Harry has also produced, including this classic book on elastic solutions for soil and rock mechanics. There's also a great book on foundation analysis and design, and he's also written one on marine geotechnics. So with that short introduction, I'm going to turn this over to Harry. He's going to talk a little bit about his commentary in his article on the urban forest that he wrote, just as kind of a precursor to some of the questions and back and forth we're going to go through during this interview.
Okay, well, thank you very much, Ken, and thank you for the opportunity to talk today about one of my favorite subjects, which is tall buildings. I thought I would perhaps introduce just summarize what I have tried to do with the articles, and if I can share my screen. Is that visible now?
Yes, it is.
Great. So there are two issues, I guess, that I've tried to address. One is there a limit to the height of tall buildings? And secondly, something that I call urban forest effects. The fact that we have in many parts of the world clusters, collections, forests of tall buildings, and inevitably there must be some interaction between them. So let me start off in addressing the first issue: how tall can we have tall buildings? And I hark back to a concept that the famous Frank Lloyd Wright put forward in 1956 about a mile-high building. And here are some of the images that came from that. And you see it's got rather an interesting structural design, which I think would pose several challenges in terms of wind loading. And then his concept of the foundation, which is really, I think, mirroring almost a tree root type of approach. But you see that inevitably there is a deep component to the foundation, and that's fairly common, of course, almost inevitable when we talk about tall buildings. I think there's a number of factors that influence the height of tall buildings, and these are in three categories. So human factors, obviously humans are sensitive to building movement and to motion of any sort. There are atmospheric pressure decreases as we go higher, and we can, in fact, if we go really high, get distortion of our views. So these are just some of the human factors. And of course, some people are acrophobic anyway. They fear heights. And so these are some of the issues that we have to take into account. Obviously, there are technical factors. Vertical transportation systems have limits. We have limitations on the structural systems and the materials and the strength of those materials. There are constrictions to construction processes. We can, if we've got really tall buildings, have a problem with the interference with aeroplanes and so on. And a not insignificant factor is the cost of real estate, because if we want to have really tall buildings, that generally implies that they've got to be reasonably wide. And that means that the cost of real estate for those buildings will be extremely high. And then in terms of geotechnical factors, obviously we have the usual criteria, but the key ones are bearing capacity, settlement and differential settlement, and lateral stability. And I've emphasized that with the sort of move towards high aspect ratio buildings, these are buildings that are very slender. They have a small base and a very tall frame. There can be lateral stability problems for the foundation as well as for the structure. So in my article, I come to the conclusion very slender, that they have possibly 4,000 meters, which is about 3 miles, may be technically feasible, but more likely, I would say 2,000 meters is likely to be as tall as we could get for residential buildings. And it's interesting, I just to finish this off, we should also bear in mind that we may in the future have buildings that don't accommodate humans. So here's one concept on the left where SOM have put forward an idea of a very tall energy vault. And in fact, quite recently in Saudi Arabia, there is a proposal for a 2,000 meter tower called the Rise Tower. And that is, I think, mooted for, it's going to happen in the next few years. So that may be the reality of the 2,000 meter tower. The second part of my contribution to GeoStrata relates to the interaction amongst multiple buildings or urban forests. And I was put onto this by an article in the New York Times, which I've sort of reproduced here. New York will sink if more skyscrapers are built. And there was concern expressed that if we kept on building lots of tall buildings, the heavy buildings, that then the ground would actually sink and we would have problems, and particularly with sea level rise. And in some cities, also the extraction of groundwater. And here's an example. I think many of the viewers may have been aware or visited Hong Kong, and there is a perfect example of a small urban forest, buildings quite tall, 30, 40, 50-story buildings in very close proximity. What I did in order to try and examine this, I took the ground profile for a real building, the Shanghai Tower, was 632 meters, about 2,000 feet, the third tallest building in the world. And on the bottom left is a shear wave velocity profile showing that it's a series of clay beds getting stiffer with depth, but still not rock. And those foundations go down about 70 or 80 meters for that building. And I thought I would examine what would happen if they decided to build another 8 buildings of a similar nature around the existing Shanghai Tower. And so the bottom right-hand diagram shows the settlement on the vertical axis and the tower number that is added on the horizontal axis. And the various lines show the settlement at various points on the initial existing tower. And to cut a long story short, the consequences are that when you have additional buildings, they cause additional settlements to the existing tower. That, I think, we can understand fairly easily. And differential settlements vary depending on the construction sequence. Now, I should also mention that I used a very simplified analytical approach here where I idealized the foundation of each of those buildings as an equivalent pier. And that enables you to do a realistic analysis without getting into excessive detail. I found, not surprisingly, that the worst effect is if you have an existing shorter building and then you build a whole bunch of taller buildings around it, that shorter building is going to suffer quite a deal of additional settlement. If, however, we have a tall building and we surround it with shorter buildings, the effect is less severe. But there are, we need to consider really the consequences of sea level rise and groundwater extraction, because groundwater extraction causes the settlement of a whole area. And we've seen this in many cities in the world. Bangkok, for one, is a classic example. And of course, sea level rise, so you've got the ground going down, the water going up, and there is the potential in the long term for flooding of lower parts of cities because of that. However, to address the issue of New York, because so much of Manhattan, at least, is on hard rock, I think the likelihood that all of New York will sink and be lost is not really credible. So I thought I would just try and summarize my views with these few slides. So I'm going to stop sharing and come back to Ken.
Thank you, Harry. I have prepared a few questions that I'd like to ask and kind of gain some insights here, but I'd certainly like to encourage everybody that's participating and watching this broadcast to go ahead and submit questions to the chat. I would certainly much rather to ask your questions than mine. I'm very curious to see, what others might be interested in, what they want to ask. So don't be shy. I'm monitoring the chat, and if you have a question, I'm going to go and either try to add it to mine or just directly ask it. So please go ahead and contribute if you so wish to do so. But let's start, Harry, with a little bit on the background of the analysis and design of foundations for tall buildings. And the first question is really, how did you first get involved with foundations for tall buildings? It's kind of such a specialty area. I mean, did you first work with someone else that had already done a tall building, or is this based on some of your past experience that was needed for one of the first projects, maybe related to your experience with elastic analysis for foundation settlements, etc.? But what was it that really first drew you into this field?
Yeah, thanks, Ken. What drew me, I think, was more experience that I had with deep foundations in calcareous sediments. And this experience initially related to offshore piling and problems that we had in the northwest of Australia with piling sort of dropping 60 meters under its own weight. And that led us on to research onto the properties of calcareous sediments and the behavior of piles in them. And then I got a phone call in 1994 from somebody that was involved in the foundation design for the Burj Al Arab, the famous 7-star hotel in Dubai. And they had seen some of the work that I'd published on that, and wondered whether I would be interested in assisting them with the foundations, because the sediments in Dubai are also calcareous, and there was a concern that under wind loading there may be a degradation of pile capacity. So that was really how I got involved. It was quite a high profile project, and it's really I was obviously delighted to be involved in that. And as a consequence of that experience, I had a number of other projects that I was asked to assist with in Dubai and in various parts of the Middle East, all of which tend to have calcareous sediments of some sort or another. And as I said, one of the key issues here was the propensity for the piling, if it's under severe cyclic loading, as you have with wind or seismic action, to lose capacity. And so that was really one of the problems. And the other thing is that because of the nature of calcareous sediments and the way that they're deposited, they tend to be fairly loose, and you tend to get lower skin friction than you would with a corresponding silica sand.
Thanks for that. So what do you enjoy most about this area, and what are the unique aspects for designing and construction foundations for super tall buildings that might be a little unique compared to typical foundation designs?
Yeah, okay. Look, I think I have to say that it's a little bit of tweaking of the ego when you see a tall building and think that you've had some little bit to do with it and the foundations, even though of course the foundations are invisible and everybody thinks about the architect and possibly about the structural engineer. But the challenges here are obviously the heavy buildings, but importantly, because they are tall and they're subject to wind and seismic loading, you have an overall stability problem that you don't have with many conventional buildings. And so you really need to consider both the overall stability and the issue of the effects of cyclic loading and whether or not that will have some influence on the overall capacity of the foundation and of course on the ratcheting. The other thing is that often when you have tall buildings, you've got a big tower and then around it you've got low-rise areas as we have with the Burj Al Arab in Dubai. And so there's the potential for very heavy loading concentrated under the tower and then lighter loading outside. So that, of course, gives you a potential for differential settlements. And so you have to try and engineer the foundations so that you don't have excessive differential settlements.
What advancements have you seen in the design and construction of foundations for tall buildings that have occurred in the past 10 years? And what's the most challenging foundation design that you faced?
Look, there's been dramatic advancements, Ken, I would have to say, since the 1990s when I was involved in the Burj Al Arab. Firstly, in terms of our ability to analyze complex foundation systems, we now have the ability through three-dimensional finite elements to model various configurations of piles to allow for the mat or the raft that's on there, to allow for walls, to allow for the effects of construction operations, excavation and so on. And we can actually sort of mirror the whole construction process in a way that we couldn't even 20 or 30 years ago. So analysis and design has advanced, and in fact, we've even got to the stage where now with some of the available software, we can model the complete structure foundation system. It's not something that's really easy to do, but it's being done in Saudi Arabia. I'm involved in one of the projects where it's being done. And it really is, in some ways, a game changer. Because normally we've had the structural engineer interacting with the geotech and we sort of tic-tac and provide foundation stiffnesses. They then go back and revise loads and come back and we have an iterative cycle of loads and stiffnesses, which eventually will get to equilibrium. Now we don't know. In the future, we may not need to do that. Now, the other areas, I think, Ken, where we've advanced are obviously with our construction processes that we're able to more reliably construct deep foundations, and not only circular piles, but now barrettes. I think well, that's what we call them in Australia and other parts of the world, big rectangular elements. And so these have been used now where you want really high capacity foundations. And one of the foundations that was put in Dubai, it took 36,000 tons and a single element, a barrette about 80 or so meters deep, 6 by 1.5 meters in dimension. So that's a tremendous capacity for a single foundation element. So these are some of the advances. And I think the other advance is that also there's been improvements in the monitoring systems that we have. We can now monitor from space. We don't necessarily have to have gauges on the building, although we still do. But you have means of remote sensing and measurement that we didn't have available early on.
Thank you. Let's move on a little bit and start talking more about what's in this issue of GeoStrata. talk a little bit of selection of the foundations. Is this something that varies depending on the country where the building is located? And what are the factors that contribute to the selection of the foundation system? Is the proximity of other buildings considered at this stage of the design process?
In answer to your last question, I'd like to say yes, but I fear no. Unfortunately, one of the mindsets that we have is that there are boundaries around our building, and we don't have to worry about what lies outside the boundaries of our property. Unfortunately, nature doesn't respect our boundaries, and so inevitably there will be interactions. And I'm hoping that in the future, particularly when we have the development of urban forests, that there will be more attention paid to the consequences of having a whole sort of area loaded by tall buildings. But at the moment, we don't have that. And as a consequence, what we've seen in some cases, and we've seen it here, I've had experience here in Australia, where you build a tall building next to an existing building, and that has a negative consequence on the existing building, causes cracking, and in one cases, it's caused a total evacuation and abandonment of an existing 10-story building. So we need to be aware of that. In terms of your earlier question, is it country dependent? Only to the extent that in some countries there are certain regulations which tend to hamper you in terms of trying to do novel and economic foundation designs. For example, in some countries you can't use piled rafts, or you can use them, but you can't take account of the fact that the raft or mat will provide you with capacity and stiffness. So those sorts of requirements mean that you have to design the piles to take all of the load. Whereas in modern design, we can at least take something like 15 to 30% of the load, in some cases more, in cases in Germany, on the raft itself. If you've got a reasonable sort of ground condition, you can save on the piles. And that, of course, these days leads to increased sustainability as well as decreased cost. So all of that, I think, is positive. So the basic principles of foundation design don't change. It's a question of whether or not we can take elements like the raft into account in that design.
I'm going to pivot a little bit and start talking a little bit more about locations. You had mentioned in the introduction, and I think what kind of drove the topic of clusters of building was to talk a little bit about New York City and Manhattan. And it was founded on rock, which we think is probably not a big problem. And then you did talk about some other parts of the world where perhaps the sediments were deeper and you would have more of a chance. And I'd like to talk a little bit more about my part of the world, which is up here in the Northeast of the United States.
Yeah.
And I noted that you have spent some time near the Boston area, sabbaticals at MIT, etc. And I remember when I was first starting out as an undergraduate, the professors at the University of Maine used to like to talk about the foundations in Boston and how those buildings were floated on this notorious Boston blue clay. And I was just wondering if you'd had any, experience or conversations about this, and just wondering if these interaction effects between the building might be more prevalent, or even changes in groundwater elevation, etc., for these types of foundations that are on these deep clay deposits.
Yeah, thanks, Ken. I did have a little bit of familiarity with the foundations in Boston when I was working with the late Bill Lamb at MIT. And I think the idea there was that if you made an excavation and so founded the building at a lower level, you were decreasing the stress on the ground under the foundation. And so you could cleverly balance the weight of the building with the weight of the excavated soil. And so that would be what is commonly termed a floating foundation. And that is fine. I mean, you still have to satisfy bearing capacity. The whole thing about floating foundations, or the major thing in my view, is that they lead to a reduction in the settlement as compared with if you had just the whole soil profile settling, because you reduce the load and then you reapply the load, and so you're reloading the clay, and so it tends to be quite a deal stiffer, 5 to 10 times stiffer than if it was loaded in a virgin condition. So that in principle is a good idea, and there have been buildings around the world that have been constructed on that basis, and some of them, pile rafts, have actually what we call compensated pile rafts. There's been examples of that where the compensation has been beneficial in terms of controlling the settlements. And one of the very early examples of this, and very innovative examples, was actually in Mexico in the 1950s, where the late Dr. Leonardo Zavert built these sort of floating pile foundations, excavations, putting piles in and then building the buildings on top of those. And of course, the excavations serve a purpose in that you also provide for basement levels as well. And so that can be a beneficial thing as far as settlements are concerned. And we have those benefits today in most projects, because tall buildings almost inevitably will have some sort of basement. So you have to carry out an excavation before you can start your construction. That, of course, that leads to a whole bunch of other issues, and one of the articles in GeoStrata talks about these, which is control of groundwater and ground movements during excavation. And these are the sort of things that with modern analysis we can now get a better handle on than we could in previous days.
Thank you. I did receive one question in the chat that I'd like to pass on to you. It's somewhat related to location as well, but this is from Santiago Caballero. He just wants to know something more about the example for the Shanghai Towers. And can you briefly go over the soils that were there? And he's curious about when settlement was measured. Was it right after construction or sometime after?
Oh, yes. Look, I'm probably not the best person to answer that, but the foundations were a whole series of very deep piles going down about 60 or 70 meters, as I recall, quite a number of them as well, and I can't tell you the actual number. The settlements, I think, were measured during and after construction, and as I recall, they were not insignificant. They were probably over 100 millimeters. And what I tried to do, in fact, with my equivalent peer analysis was to calibrate my single equivalent peer analysis with the measured settlements. And I used as a basis for estimating the settlement the shear wave velocity profile that had been measured and reported. And I'm a very strong advocate of actually measuring shear wave velocities for foundation design purposes. It's something that we do increasingly for liquefaction assessments, but to my mind, shear wave velocity measures indirectly the stiffness of the ground in situ. So it involves very little disturbance of the ground, and it also identifies any anomalies in the ground that we may not pick up with normal sampling. So I can't really provide you with too much detail. I'm sorry. I guess time would prohibit anyway, but the details, it's a few months since I did this analysis, so the fine details I've forgotten. But that's the general process. And certainly this was a tall building that settled way more than the sort of 1 or 2 inches that you would normally think about. And that's one of the criteria, of course, that we have to cope with, is that if you've got buildings that are, hundreds of meters tall, you can't expect expect them to only settle a few inches, 2 or 3 inches. Normally, we find that we can cope with 5 or 6 inches without too much problem, as long as you don't have major differential settlements.
I got another one from the chat that I think is quite interesting. He's asking about a case of large pile group foundations and wants to know if you have any knowledge about the performance of piles in the middle. Do they really work, or do the corner and perimeter piles take the majority of the load?
Okay, that's a good question. When you have small pile groups and you've got a reasonably rigid cap, then the center piles tend to take a bit less load than the outer piles. It's just that there's more interaction effects between the piles. However, when you've got a very large pile group, the center piles work almost as hard as the outer piles. What they don't, in terms of dead loading, they probably take almost an equal amount as the outer piles. The outer piles tend to work harder when they're resisting overturning moments and lateral loadings due to wind and seismic effects. But the thing is that when you've got a very large pile foundation, the mat, even though it may be 3 or 4 meters thick, is still relatively flexible in relation to the overall width of the building. And so that rigidity of the foundation that you have with small pile groups, which allows you to sort of have that the more rigid piles outside and the more flexible piles inside, doesn't actually happen with really large pile groups. And so, yeah, the piles in the middle, and particularly, of course, if those piles in the middle are near lift cores and so on, they actually can work really hard as well as the outer piles.
Eunice Ali wants to know, in the case of rock foundations, is it feasible to adopt a piled raft foundation for a tall building?
If you need to, yes. Why not? My criteria for the adoption of a piled raft is, firstly, will the raft provide you with a reasonable measure of capacity and stiffness? Obviously, in rock, the answer would be yes. The second question is, do you need piles? Because if the rock is really hard, you're replacing 100 MPa rock with 60 MPa concrete. That may not be the smartest move. Or you may, of course, need the deeper foundations for lateral stability. But in principle, yes. And we've obviously used in the Middle East foundations, the rock has been soft rock. It hasn't been hard rock, but it's been rock with, forgive me for my SI units, but unconfined compressive strengths of 1 to 4 megapascals. So it's a sort of really like a very weak concrete. But there you can get quite a deal of capacity. I think in some of the Middle East buildings, we've got maybe 15 to 20% of the load, the dead load and live load, carried actually by the raft itself.
I have one more question from the audience. I'm not sure if I quite understand it. He may be way ahead of me in terms of what's going on with the physics here, but it's kind of relating to the forest of buildings. So I'm going to ask it and then see if I can try to interpret a little bit. But he's saying, does a forest of tall buildings affect the weather? I'm wondering if he's referring to maybe wind. If you've got a forest of tall buildings, maybe the wind loadings are affected by the presence of the other buildings or something like that. Or maybe if maybe there's something else in there that you'd understand better than me, but I didn't quite get it.
Yeah, well, I guess it depends on how you define the weather, Ken. I don't think it will influence the atmospheric conditions to a great extent, but I think perhaps locally, and certainly in terms of the effects of wind, for example, on people on the ground, it can obviously have a significant effect. And depending on the orientation of the buildings and the direction of the wind, you can have wind funnels. I mean, we've seen this. I'm sure all of us have seen this in the cities, that you get into a place where there's like a funnel of wind through gaps in the buildings, and it can lead to discomfort. But in terms of the general weather pattern, I'm not sure that it can. It's perhaps something that an environmental engineer might be more capable of answering properly than I can. I can see that there would be micro effects. I don't know that we could control the weather by building urban forests. But that I guess is a question for the future.
Yeah, I think I was just thinking as that might affect the foundation design, whereas the rest, I'm not sure, has much impact on foundations in terms of the
let me just
itself.
say, Ken, that in terms of wind affecting foundation design, one of the I guess the developments over the past 40 or 50 years has been our ability to do wind tunnel testing and to actually look at those localized effects of wind on our new building and also on existing buildings. And so that's a facility that we have now with the developments in wind engineering. It's a really interesting area.
I'm going to get back a little bit to some of the questions that we looked at previously. For designing the foundations of tall buildings, are there any special practices for risk management that could be implemented to mitigate the foundation interactive effects between adjacent tall buildings? I think we already talked about the idea that really we're not sure how much consideration this is given at the design stage, but are there some collective risk management practices that could or should be implemented?
Yes, I think gradually people are becoming more aware of the potential effects of their project on existing projects. And there is now, in some cases, particularly when you're dealing with sensitive historic buildings around a new building, there is a tendency for monitoring, condition monitoring of the existing buildings to occur, just so that we make sure that our new construction will not have a deleterious effect on the existing one. So the monitoring of existing buildings is something that I think is going to be a little more prevalent. In terms of our own building, I think I'm a very strong advocate of measuring the settlements during construction. And we need to have predictions of what we anticipate to be the settlements of our building as it's being constructed, and to ensure that, or hopefully ensure that what we measure is what we expect. I've had a case in Hong Kong where we did that and we found that the settlements were larger than we had anticipated. And what that led to was a halt in the construction and an upgrading of the foundation system because there were obviously some problems with it. It turned out to be the piles were not that well constructed. And so that, I think, is another aspect of risk management for our own project, that we need to make sure that the behavior of the foundation and of the structure, if we're monitoring the structure, is consistent with our expectations in design.
Another question from the chat that's kind of related to design and construction, but he says the pile raft foundation systems involve mass concrete. The control of the heat of hydration would be a prime challenge. Do you have any proposal to control the situation as not to exceed ACI limits?
Yes, again, a good question, and absolutely correct question, because some of the rafts we're talking about can be 4 or 5 meters thick, so we're talking 18 feet thick. And I believe, and this is not an area of expertise, but I believe in those sort of cases, they have run cooling pipes through the concrete. I'm aware of this, I think, with even some of the Middle East buildings. The Burj Khalifa, for example, that was 3.7 meters. So that's around about 11 or 12 feet. So that was quite thick. And yet, just to emphasize again, despite that thickness, there was a differential settlement between the edges and the middle of about 15 to 20 millimeters. So, even though that raft is very thick, it's not totally rigid. But yeah, the heat of hydration is a major issue, and it's probably an issue, although we don't take it into account as much with the deep foundations. Some of the really big barrette foundations that we construct, there can be a significant heat of hydration there, but it's buried.
As far as foundation testing and evaluation, kind of going back, to the urban forest, are there data available to verify and validate the simplified equivalent peer analysis? That might include results from computer modeling, case studies, observed performance, etc. And I'm even wondering if maybe I should have asked this question the other way, because maybe the simplified equivalent peer analysis serves to validate some of the results from computer modeling. Maybe they work hand in hand.
Absolutely right. And I mean, this is really why I spent time trying to develop the equivalent peer approach, simply not so much as the final design approach, but as a preliminary design approach, and also as a means of checking some of the very complex numerical analyses that we do now with 3D analyses. And yes, I mean, when I did develop this, Ken, I did take a number of case histories and try and model them simplistically as equivalent peers, and checked that the settlement that I got using the available in situ data to get stiffness of the soil, that was consistent with what was measured. So there has been some calibration there. But when you, and I urge my young engineers to do this, when you get a problem, sit down and draw a simplified picture of it. And even in the case of the Burj Khalifa, you've got 828 meters of structure, and you've got about 50 meters of piling. And 50 meters of piling is deep, but in comparison with the height of the building, it's pretty shallow. And you see that basically you can treat that foundation system, it's almost like a little sort of pier, an enlarged size pier. And that's how it actually behaves overall. I mean, obviously in detail, you have the piles doing their own thing, but overall, the equivalent peer often captures the key aspects of behavior of a pile foundation.
So my next question, and we're getting kind of close to the end here, but it's kind of related to durability, service life, and a topic that I think is kind of popular, foundation reuse. And this may relate a little bit to the urban forest if you find that you might have a problem and you need to retrofit a foundation. But can the foundations of existing buildings be retrofit either to support additional stories or additional loads that may be anticipated? Can those foundation systems be reused and upgraded to meet these needs? Do you think?
And the answer is a resounding yes. And I mean, it's been done on many occasions. That people have repurposed existing buildings and added on to them, particularly, I guess, with the high cost of real estate in urban areas these days. It is attractive for a developer to try and maximize his return by having as much real estate sellable or rentable as possible. Now, there are dangers and cautions that have to be exercised here, because if you start interfering, let's take the case first of an existing building with foundations and you want to augment the foundations. The ground under the existing building is fairly highly stressed, and when you drill holes or put piles in, you are disturbing highly stressed ground, and so there will be an effect on the existing building. And there's been a classic example of that in your country, in San Francisco, with the Millennium Tower. I think it's been very well publicized that attempts to stabilize the settlement of the low side of the Millennium Tower resulted in additional settlements because of the construction-related ground movements, which then impose themselves on the existing foundation system. So yes, you can, of course, and we do this with underpinning all the time, but you have to be careful that you do this very judiciously, and that, again, monitoring here is absolutely critical, so that you can see step by step what your actual construction activities are doing and stop if it's going beyond the bounds of acceptability. The other case of repurposing, we had one again in Dubai, where before the financial crash in 2008, piles had been installed for a building. That particular project was stopped, and then a few years later, it was started with a new developer who had a different concept, and there was then the need to try and incorporate the existing piles, of which there were quite a number, into the foundation system for the new building. So there was a process of excavation, of putting in new piles in appropriate locations and making use of the existing piles to try and come up with an integrated foundation system. Yeah, look, that is happening and is bound to keep happening, because these days most of the buildings that we construct seem to have a life of 40 or 50 years, and then somebody comes along and says, this is getting old, we need to replace it. So that will keep going on.
One more question from the chat. It's kind of related to foundation testing, and he wants to know if you could elaborate on pile load testing practice for tall buildings. What are the common methods, and how can pile load testing shape the foundation design?
Yeah, that's a very good question. One of the things I should have mentioned before, Ken, in relation to the major developments, has been the developments in pile load testing. And I think a real game changer has been the Osterberg cell that the late George Osterberg developed. That has enabled us to, I think people are familiar with the concept here, that we basically put in one or more jacks within a pile, and we pump up the jacks, and so we push down on the bottom part and push up on the top part. And what that enables us to do is to put very high loads on piles, firstly, and also to mobilize the bottom part of the pile, which normally top-loaded piles may not be able to mobilize the full end-bearing capacity of the piles. So that's been a game changer, and it has allowed us then to firstly test larger and stronger piles, and secondly to get much more detailed information on the skin friction and end bearing along the whole pile, not just on the upper parts of the pile, which were doing all the work when you're doing top loading. And that in turn, I think, has influenced our pile design. We again, I'm doing a project in Brazil where our initial predictions of skin friction were quite conservative as compared with what we found with a series of almost 20 pile load tests. And so that has shaped our design and enabled us to do a more efficient design than we would have otherwise.
Thanks. In the last few minutes that we have here before we turn this back to Brad, I want to give you a chance to kind of speak freely and speak your mind. But what do you think the future holds for foundations of tall buildings, and do you have any closing comments that you'd like to make?
Look, I think for the foreseeable future, we will be building tall buildings. I think even in my not so heavily populated country here and in the city of Sydney, real estate and housing is a major issue here, and the difficulty of housing. And the government is encouraging developers to build multi-story buildings so that we can accommodate more people. So I don't see that there will be any reduction in the human desire to build tall buildings. And that means that foundation designers will inevitably be busy for the next few decades. The other thing is that, as has happened with a lot of other types of building, we will have to encroach on less desirable ground conditions that we may have thought previously we didn't want to build on. Now we may have to build on because of urban pressures. And so that, I think, will keep our foundation designers in business, certainly over the next few decades. I think that's basically it. So I don't think we're a dying breed. I think we probably need more.
I did get one more question from the chat.
Yeah.
He's kind of related in group pile behavior. He wants to know if there's a way on site to measure group pile action for foundations of tall buildings, either during or after construction.
Yeah, good question. It's not really easy on the actual foundation itself. I don't think so, to be honest with you. Because normally we don't have when we install the piles, we don't have load on the piles unless you deliberately go ahead and load one pile and measure the settlement of that pile and the piles surrounding it if you're really concerned about interaction effects. But in practical building projects, I don't see that this would be feasible, mainly because firstly, the logistics of loading piles individually and measuring, and secondly, because time is money for your developer and the contractor, and so anything that delays them is not likely to be popular.
Thank you. Not sure if Brad is available, but we've kind of come to the end of our time, and I assume you have no other closing comments, and I've got no other questions from the chat. So I'm trying to turn it over to Brad. Are you there? Yeah, I think he went to a different commitment. So I guess thank you for the time that you took to speak with us. I just note that it's very early in the morning over there in Australia, and it's also summertime. So
yes. Well, thank you, Brad. And look, I really do appreciate the Geo-Institute giving me this opportunity. And I mean, more generally, the Geo-Institute is such a pivotal aspect of our profession. And I can only congratulate the people that run it and are involved in it, because it really is a highly influential group. And certainly, personally, I have benefited greatly from the ASCE and from the Geo-Institute part of it. So thank you very much.
Okay, thank you, and thanks for participating in this GeoStrata Extra, and for your contributions to the theme issue. Thank you very much.